Hey, everyone. We're here to talk about microservices using relocatable Docker containers. I'm Thorvald. I've been with Medallia now since 2010. This is Mauricio. He's been here since 2011. He was one of the first hires here in Medallia, Argentina. Now, one thing, I don't actually speak Spanish. And to make it even worse, I have a tendency to speak English really fast. So, if I start going really, really fast, if you just, blabber something at me in Spanish, I'll take the hint. Okay, so who's Medallia? Medallia was actually started in 2001, and Medallia has a very simple business goal. We're trying to make companies listen to their customers and enable them to actually understand what their customers are saying about them. Now, all of you have at some point stayed at a hotel, flown an airline, got to a store, and your interaction with this has been either good or bad. And what we allow companies to do is to figure out how that interaction went. And if it was something that went well, where you think come back and say, wow, that was awesome, and you go tell it to other friends, we want them to know so that they can go do more of whatever it was that made you happy. And let's say you go to an airline and they cancel your flight, they cancel also the next flight, they don't give you a hotel, and in fact you had a really miserable experience. You will also tell all your friends and you will tell them, never fly this company again. That's also really bad. So we will allow them to capture that too, and actually reach out to you really quickly and say, hey, we're so sorry, we messed up, here's 40,000 bonus points, please fly us again, and don't tell your friends about this horrible thing. Tell us about the 40,000 bonus points instead. And this works, and we're now seeing that all the companies we have partnered with are growing, 40% faster than competitors who don't care about customer experience in the same way. We are a global company. Our headquarters is in Palo Alto. We have a developer office here in Buenos Aires. We also have offices in London, Paris, Hong Kong, and Sydney, and Melbourne. If we take all that and translate it to what it means for an engineer, it is that we collect, we analyze, we display terabytes of data, structured and unstructured data, for all of our clients. And we do it in real time. And we have a lot of fun doing this because we are not afraid of trying to use state-of-the-art technologies. We constantly push on these technologies to make them better. And if you look at our analytics engines, both for structured and unstructured data, we are at this point ahead of the technology curve, both for the industry and for some of it actually for technology industry as a whole. And that's cool, because at least personally, I like working on bleeding edge tech. Now, topic for today. If you think of an entire business as sort of an inverse pyramid, at the top of it, you have the user-facing stuff. This is the stuff that's extremely specific to the business vertical you're in. For us, this is where we talk about, okay, how do we actually capture this feedback, social media and so on and so forth. Below this, you typically have a slightly smaller block of things, which is data crunching. This is where you actually do your analytics. This is where you do text analytics in form of machine learning. This is structured data analytics in form of some sort of in-memory or otherwise databases. And on the bottom of this, you have the foundational stuff. Foundational stuff is how do we actually get code out there, how do we deploy it, how do we hook it up, how do these things communicate, where do you store things. Now, the further up you go in this pyramid, the more business specific it is. But at the bottom, and which is what we're going to talk about today, this should actually be applicable to any company. So our hope is that what we are talking about today, you can go and bring with you, even if you don't end up being interested in Medallia for some reason. You can bring this wherever your journey takes you and actually use some of this in your work. So, to get started, let's first talk a little bit about infrastructure. Infrastructure is that wonderful thing that runs your code. Now, if you're a small company or you don't have large computational requirements, there's a wonderful thing called Amazon. And many, many others like it. And it's fantastic. If you just want to get something up and running right now, it's really, really hard to beat. But once you start doing large-scale analytics with really large amounts of data, and you want to process and churn and chunk this and slice and dice it in real time, Amazon is no longer a good fit. Because for Amazon, if you actually want to rent the entire machine and you want to rent it 24/7 and you want to rent it for a year, it's about 4 times as expensive as just buying that server and putting it in a data center. That's for 1 year. Let's say assume you keep this server for, say, 2 years. It's only a lot more cost effective to host it yourself. Also, if you do host it yourself, you can buy a lot better hardware than what Amazon has available. So we built our entire infrastructure after a few very simple principles. The first is use commodity components. And the reason for that is we want to make sure that for everything we use, there's multiple vendors. Multiple vendors means they compete with each other. Multiple vendors that compete means the prices are low. I like low prices. We want to have open standards, because that means if we buy one type of component today, we buy another component tomorrow, they talk the same standards, we can actually interchange them. We need fully automated provisioning and reinstall. We don't want to maintain all of these independently. We want to have something that just plug and go. And last, we want it cheap and scalable. When I say cheap, that's not because I want to buy cheap hardware, that's because I want to buy more hardware. And the more cost effective I can make each server, the more servers I can buy. And I like large clouds of computing power because that's a lot of CPU power, a lot of memory, a lot of network bandwidth, and I can do much more data crunching. The other design goal we have is to avoid special machines. And almost any data center design you look at has a few machines that are sort of the golden cows that you cannot touch. And everybody knows that it's there. Nobody really knows what it's doing or how it works. But everybody knows that if you turn it off, everything stops working. And usually this is some box with a logo on it that was bought from some vendor that maybe makes 10 of these a year, and they installed it 3 years ago. We can't do that. We can't have these special boxes that are so precious that we can't even maintain them. So we have a basic design principle, which is every single component, and we mean everything from load balancers to databases to actual computational things, must be able to run anywhere in this computational cloud. And we move our redundancy to that layer. So instead of buying one box that has 2 power supplies, 2 network supplies, multiple RAID disks and all that stuff, I buy the cheapest service I can get. Single power supply, single network supply. RAID, nah, don't need that. And you move your redundancy to the application instead. Now your hardware becomes cheap and fills this cheap and scalable thing. And instead of buying one server that's super redundant, I buy 3 servers. So the most important thing for everything is keep it simple. And the reason keep it simple is a basic design goal is if you have a simple architecture, then it's simple to understand. Hopefully by the end of this presentation you'll actually all understand how our basic architecture works. Enough that you can go replicate it. Simple also means it's really easy to bring in new people. And simple means that when it breaks at 4 a.m. in the morning in a critical way, it's really simple to repair it. And if you've ever had a phone call at 4 a.m. in the morning, simple is awesome. So how do you actually scale this? There's a wonderful quote, if you go Google for it, which is treat your servers as cattle, not as pets. And it really goes towards don't have 100 servers and you give each of them a special name. You sort of log into them tenderly and check that they're doing okay every day. When there's a package that needs to be installed, you go take each of your little pets and give them their little nibble of packets. And for some reason you need 5 people to maintain 100 servers. And that's all they do. They really log into them every day and check that they're okay. It doesn't scale at all. You need to treat your servers as cattle. Everybody is the same. They have unified names, usually coming from their IP address or some other random thing. And everything is completely identical. There's no unique personalities at all. We've actually taken this to the scale of we have entire data centers be automatically reinstalled. That's how we maintain the servers. You want to add a package, you reinstall the servers, all of them. At that point, we can guarantee that at any given point in time, they're always identical. And it takes us about 20 minutes to reinstall an entire data center, switches, networking, servers, everything. And that's rolling to avoid downtime for the actual customer. So we have standardized rack design. We have 22 compute nodes with Intel CPUs on Linux. We have 8 storage nodes with Intel CPUs on Linux. A little bit less CPU on the storage, a lot more storage on the storage nodes. And we have networking. Our networking is 4 gigabit end-to-end, and it runs on a switch that has an Intel CPU and runs Linux. Specifically, it runs Cumulus, which is a Debian spin-off. So is Ubuntu. So I can actually take the exact same package for whatever and install it on my compute nodes, my storage nodes, and my switches. It's actually really interesting to log into the switch and see that it looks like a Linux box with 32 network cards. It's remarkably easy to maintain all of this. So,
yeah, microservices. Okay, so we have all this cool infrastructure in place. We have a very powerful servers. But now what we want to aim is to optimize for developer freedom. So now, taking from this cool quote, the idea is that we can take delightful implementation of a fresh idea in one day. The idea is that the time you take to put a new feature in place should be much more faster than in a regular way. So the microservices architecture actually enables that. So it removes the roadblocks to release or to deploy if we compare that to a regular big and monolithic system. Also, the idea is to remove dependencies between teams. So if my team is, for example, in Medallia Text Analytics, I want to deploy a new feature. I don't want to wait for the whole system to be updated to push my new release. So the idea of microservices is to actually decouple the feature from each other, and again, optimize for development freedom. There's a very interesting concept here, which is a one pizza team. The idea is that the team shouldn't be filled at most with one pizza. That's 1 or 2 persons. And this is actually impossible if you have 100 developments modifying or touching the same code base. If you have one big application touched by a lot of developers, you can't handle the complexity without this microservices thing. So the microservices, this architecture actually made the code base easier to understand, because now the whole application is split in smaller code bases with a very narrow responsibility. And it's actually reduces the ramp up you need to start pushing changes in an application. It mitigates the fear of change. So if you have an enormous code base, you need to touch something, you're not pretty sure if that's going to affect something else in an unexpected way. And there's another very good feature or advantage of using this architecture, which is that you can scale each component independently. So for example, raise your hand, how many of you uses Spotify, for example? How many of you pay for it? All of them? Cool, that's great. But at the same time, you don't have the same requirements for the people that uses it than the people that pays it. So if you think about the services, you have a billing service, which is going to be, it's going to have much lesser requirements for scale than the actual services that are streaming. And it also simplifies the adoption of new technologies. If one day I want to start migrating my service to a new shiny framework that is released recently, or change the programming language maybe, you can do this. If you have a big code base, one big application, one big technology, you can switch that easily. Overall, the idea of this architecture is to increase the developer agility. But this has its problems. So it actually multiplies the risks of running one single monolithic system. So if you have one monolithic application, you have one log file, you have one set of metrics to take a look at. Now you have multiple. You can have hundreds of, maybe thousands of different services you need to run. So definitely the infrastructure needs to support the microservices development. It's not going to be the same as coding on a monolithic system. And these foundations are actually required if you want to pursue this architecture. These microservices are going to be talking to each other, so you need to have a common meaning of communication. You need to set a common transport media and how the messages are going to be moving between the several services. Monitoring metrics and log consolidation is super important here. Again, you don't have one log file, you have multiple, and you want to correlate the events that are happening in your microservices. But what's more important also is to deploy each service independently. So you need to have the infrastructure to support that developers will be able to deploy new versions independently from the rest of the system. So, Docker. If we are going to let everyone deploy some solution, some microservice, we need to standardize that in some way. We don't want each team to re-implement all the deployment process or implement how the logs are consumed. So the idea is that the foundation of the microservices cover this. So you have one team developing all the components that needs to be ready to put a new microservice in place. And we also need a common runtime format. So if you have a team deploying, coding in Java, other coding in Node.js, you want to have a common runtime format because you don't want a mess of different technologies running there. So the containers actually gives a very good tool to abstract that and have the same process running everywhere. So this Docker thing is actually a couple of technologies that are present on the Linux kernel since time ago. Docker simply productizes it and gives several tools to make it easier to deal with those. And these features are Linux cgroups, namespaces, and union file systems. So the cgroups and namespaces basically allows you to isolate your process from the rest of the system. And union file systems are a very good way to ship the root file system of a container in an independent way. So what actually Docker allows you, or it enables you, is that, for instance, in the past, if we want to have different processes running on the same computer, we tend to have an hypervisor running several virtual machines. But this schema has a problem, which is that you need to have a guest operating system running for each of your applications inside the same server. This has a very heavy burden regarding resources. It's overkill sometimes. And also, all of the, for example, in this diagram, you have 3 applications, 3 microservices. Now the team responsible for those microservices needs to also maintain the guest operating system. So for example, if you're running Node.js, you need to take care of the dependencies, and the operating system you're using has the updates, the security updates it needs. So instead of that, Docker allows you to share the same operating system, share the same kernel, and only ship separated applications and libraries. So in a way, it's a lightweight virtual machine. It keeps your process isolated, not as isolated as using virtual machines, but you don't have all the burden of having a separated guest operating system running. So again, this is a very good way to have services containerized and deployed in a consistent way. Doesn't matter you are running Node.js or a Java application inside your container. The container can be deployed in the same way. And what's most important is that you are actually running on production, on testing, and on development the same artifact. So the same container you are building for these 3 environments are basically the same. And your container also only includes your application and not the entire kernel and operating system. Still, it has some problems to achieve full mobility. So what's that? So if you remember one of the principles that Thorvald mentioned, we want that every component, every service, must be able to run anywhere. So Docker allows that, but it has a couple of problems that Thorvald is going to talk about.
Sure. So one of the problems that we've actually attacked and tried to solve is the ability, or the problem with relocating the services that are really difficult to relocate. Specifically, think that you have your data center firewall. This is a large appliance. It really is a hands-off thing and not something you want to have automated modifications to. It sort of defeats the purpose of a security barrier. But the firewall, when a request comes in, needs to send the request after a load balancer. So let's say we run this in Docker, we run it on the machine. There's this Nginx. The request goes from the Nginx onto, well, talk to Zookeeper, figure out, okay, where is this application I'm actually going to talk to? Nginx then from Zookeeper learns where the application is, forwards this to the host that runs the application, and forwards the request. Now, when the application started, it needed to talk to Zookeeper to figure out, okay, there's Zookeeper, here's where I am, so that Nginx now knows where to find me. There's a problem. What happens if one of these two machines die? Well, for the Nginx machine, we can always take the Nginx process and start it somewhere else. But now it has a new IP address. So somehow I now need to update my firewall to point to this new IP address. That means automating the firewall, which is pretty blatant security violation. The other one is, hey, what happens if my Zookeeper dies? Well, Zookeeper usually have 5 of them, right? So chances are if one dies, it's not a problem. But sooner or later, you do need to restart that 5th node that just died somewhere, and you need to either update every single instance of application you have to point it to this new IP address, or you need some other way. Now, what most people end up doing is, hey, we'll just put the Zookeeper IP addresses in DNS. Wonderful. You have just made DNS that critical service that cannot die and cannot move, because you cannot actually use DNS to find your DNS servers. So, how do we actually go about that? Well, Docker's networking is not actually quite that transparent. It's really transparent and easy to use for a developer. If you want to run 7 Docker containers on your local laptop and you want to connect them up to each other, there's good built-in support for hooking these up. Now, if you're in a data center, you have these 7 Docker containers, you want to run them on 7 different machines. All of the tools that Docker gives you no longer work. And the way Docker does networking is it does natting. Wonderful, it does masquerading. The same stuff that your home firewall, that little thing you got from an ISP does, that's how Docker does its networking. It's reintroduced dead technology to the data center. Yay. Yeah, I loathe the masquerading I have on my home firewall. I'm also not very fond of the one that now runs in my data center. There's a lot of projects that are around to try to address this. There's Socketplane, there's the Calico project, there's Pipework. All of them either run as co-processes, they run alongside Docker, and they try to modify Docker as it runs, which has the problem that the network is not actually up when your application starts. The network will be up just a few seconds after your application's up. This is wonderful until your application actually starts up and tries to figure out what its address is, because the network isn't up yet. They also have serious compatibility problems with most of the orchestration tools. If you look at most of the off-the-shelf orchestration tools, they don't play well with these technologies. So you end up having to have a whole bunch of scripts, and you have to modify all the Docker images to support these orchestrations. So we actually went over a different direction. We modified Docker. And we told Docker, hey, this natting and all this stuff, this layer 2 technology, this attempt to bridge Ethernet, that's not where we want to be. We actually want to do routing. Full-on IP routing. At some point in time, yes, it was true that switching was a lot faster than routing. It's been a while. These days, every single piece of hardware you can buy that does networking, be it either the little network adapter sitting in your server or the switches, do routing and switching at the same speed. There's no speed difference anymore. So doing the full-on routing decision actually gives you a lot of freedom. So we told Docker, hey, just give every single container a static IP address, and as you move it around, we'll move the IP around as well. That does have a problem though, because for you to do IP routing, you actually need everybody to have a routing table. So let's say we have this container running here, and we've actually set up routing on every single machine to say that to reach 10.123, this is the direction you send it in. Wonderful. Then I move it. Yeah, absolutely all my routing information, and I do mean every single one of them, is now wrong. This is a bit of a problem. Thankfully, though, it is a problem that was solved about, what is it now, 30 years ago? There's a whole set of routing propagation protocols. The one most of you actually use every single day is BGP. It ties the internet together. Because it turns out the internet has the same problem. Nobody actually has a static route table of this is how the entire internet works. Imagine that, right? Every time somebody wants to hook up an additional company to the internet, we have to call every single ISP in the world. That wouldn't scale. So all of these are based on link propagation or some sort of forwarding information. And the basic version goes, it's basically saying, hi, I can see Mauricio. Now, since all of you just heard that, you know that to reach Mauricio, all you have to do is talk to me. This is the most basic version of it. And they basically propagate around the same thing. OSPF is one of the interior ones, so they're designed not to run the internet, they're designed to run one site. Normally you run it only on the routers. We run it on all the switches and all of the servers. So for us, when a container starts, well, since we run the servers as if it was a router, what it looks like is a server just showed up. OSPF does have computational overhead. It needs to do shortest path first for 30,000 nodes. In today's world, that's absolutely nothing. It takes a few milliseconds. Now, it does take us about a second. Our worst case test for this was we took 30,000 containers, 50,000 of half the data center, 50,000 on the other half, and then we moved them around. It took a second to converge. Most of that time was actually spent updating all the route tables on the switching chips. Turns out that doing the recomputation took a few milliseconds and then took a few hundred milliseconds to push all this data out to the routing chip. So it is though really, really fast. Now, how can we actually tie this back to where we started, which was the infrastructure? Well, that automatic reinstall we talked about, how does the server actually boot if it doesn't have an OS or it doesn't have anything? Well, it goes out to the network and says, hello, who am I and what should I do? Okay, normally you do this through a DHCP server, which is one of the others, black boxes and so on and so forth. We run this as a Docker container. In fact, we run 8 of them, just because we could. So they're fantastically resilient. So when a server boots up, it goes out, it sends it to this IP address and says, hello, what should I do? Gets back a reply, here's what you should do, here's your OS, please install this, here's your configuration, I've derived it based on where you're placed in the network, and so on and so forth. We actually take this one step further. Because this basic bootstrapping process, we have that routed between the data centers. So if I set up a new data center, all I have to do is roll in blank hardware, turn it on, make sure that the data center network core is tied to one of my other cores anywhere in the world, and this data center will now boot up. Both the networking gear and the servers will boot up, get their configuration, and self-reinstall. So I can take completely blank hardware, slot it in there, and it just installs itself. Minimum hands-on, and very scalable. Now, the other problem you have in Docker is storage. So let's say that I have an application that talks to a Postgres database, and I have this wonderful thing that I have static IP addresses, which means if this server dies, I can start my Postgres server over here. Wonderful. The application can still reach the Postgres server. There's only one tiny problem. The storage is still in the server that just died. So yes, you can absolutely reach your database, there's just no data in it. So this is a design decision in Docker, which is it's designed to be ephemeral. Docker does really well with stateless services, things that are not expected to survive a moving or a reboot or anything like that. Docker, by its design, when you start something up, you have a local file system, you can write to it. If you stop this instance, start a new one, it's gone. Now, there are solutions for this. You can use persistent volumes. They're still local to the machine. There are proprietary solutions where you can go out to one of these large vendors and you can buy this 12 box for a really amazing amount of zeros. And they have some trade-offs. You have the iSCSI-based solutions. Yes, you have to talk to one of the large vendors. Implementation, you can do NFS. NFS is really easy. It's also really slow. And again, you have to talk to this large vendor, and now not only is it slower, it's more expensive for some reason. Or you can go to parallel NFS, which is combining NFS and iSCSI, that use NFS to do metadata decisions and use iSCSI for the data access. Right. We tried it. We did. It mostly sort of worked half the time. It's probably the lowest availability I've ever seen in a large black box. And the problem with all of them is, if you run out of space, yes, you can add more hard drives. You can add racks and racks and racks of hard drives to these things. If you run out of performance, that's a separate problem. Because almost all of these are designed with one large head, which is sort of where you hook up all your stuff to get to the data. And if that one's out of performance, then that's it. Now you can buy 2 of these things, and now you can say, okay, I think that these Docker images are going to use roughly half, so I'm going to put them here, and these are going to be here. Hope you're right. Because if you're not, you're going to have to move things between these, which is a major pain in the... yeah. Unless there's this thing of SLAs. If you've seen any modern hardware, they come with 4 data centers, 4-hour SLA, which means if you have a problem, you call somebody, within 4 hours, they will have a tech on site. If you have a promise of 99.5% uptime, that's about 11 minutes per month. So these 4 hours, nope, can't wait that long. So buying a large black box where your best recourse is to call somebody and you have no idea what goes inside it isn't really a good solution, at least for us. So we've actually gone with open source based distributed storage with Ceph. Ceph is based around a very simple idea. You take a whole bunch of completely standard servers. They do have a lot of storage, and you distribute storage among them. You make sure you have multiple copies of every single piece of data, so that if a server dies, then boo-hoo, you have 2 other copies. And since it's distributed, then, well, you never run out of performance because you're going to talk to all of these servers in parallel. So if you run out of performance, you just add more of them. So the simple version of Ceph, there's a wonderful large technical paper for this. I do recommend it if you're so inclined. Is that instead of thinking of, okay, you have a metadata server, and for every time you want to access something, you talk to this metadata server to figure out where it is. Ceph goes a very different direction. You have a fixed number of placement groups. Let's say we have 30,000 placement groups. Now we have also a fixed number of drives. The only thing you do, and all the metadata you keep, is the mapping of placement groups to drives. Now, when a client wants to actually access something, it has rules of how it should compute which placement group it should use. So in its basic version, that's basically taking the hash of the image name and the block number. Ceph uses 4 megabyte blocks. Modulo the number of placement groups. That gives you the placement group. Now you go look at the map to figure out where this placement group is. The advantage of this is that, let's say one of these OSDs dies. And yes, that does happen all the time if you have a few thousand of them. But the only thing we need to now update is that this placement group is no longer on this physical drive, it's now on this physical drive. And since you have so many of them, there's a minimum amount of data you have to move. And it also means that in a hot path, you never communicate with the metadata servers. So on our test cluster for this, the OSDs are busy, but the metadata servers, which we over-provisioned slightly, are in fact mostly idle. They do very little work. So if we go back to the same problem, and I'm using my database server, well, it will actually work because it's connected to the same distributed storage. And if you run with this 3-replica solution, then you can actually lose, in our case, 2 full racks worth of storage servers, and we're still up and running. Now, if we use 2 full racks of storage servers, there's got to be some panic involved, but we're not down. So, the thing is, all of this so far is wonderful, right? It allows you to move things around. We still have a human being doing that. Somebody's saying, okay, so I want to take it out of this server, I want to put it over here, I want to hook up this storage, and so forth. You try to do that at scale, you're going to have a fat-fingered accident really fast. If you're not familiar with that, it's called a typo. And that's why you try to move a database and you accidentally hook it up to the storage for another database. And all of a sudden you have 2 databases hooked up to the same storage. You now have 2 very corrupt databases. So you really don't want to have human beings doing this, and especially not at 4 a.m. in the morning. Been there, done that. So you need some sort of system that can take care of this for you. We are using Aurora and Mesos. They both came out of Twitter. Aurora is still primarily Twitter maintained. Mesos is now its own company called Mesosphere. Mesos is a cluster abstraction system. All it does is keep track of what resources do you have in your cluster, are they up and running right now, and who is actually using them. That's all it does. On top of this, or running next to it, you have Aurora. Aurora is a scheduler. Aurora looks at all the resources that Mesos has gathered and says, okay, so you want to run this new job, you need 2 CPUs and a gigabyte of memory, and you want 3 of these. And most likely you have some additional rules, such as, if I want to run 3 instances of something, chances are I want to run 3 instances for redundancy. Please don't run them on the same machine. In fact, please run them on separate racks. Aurora has very good rules for all of this. So it will then go to Mesos, look at what's available, figure out, okay, so I can put it here, here, and here, reserve that, and tell Mesos, okay, on my behalf, please log into those servers and run these jobs. And Mesos goes and does that for you. The wonderful thing about Mesos is that Aurora is just one of the schedulers. We picked it because it has fairly good Docker support and runs well with the resource allocations we need. But there's also Hadoop schedulers, storage schedules, and so forth. And you can then have your large compute cloud be used for all of these things mixed and in between each other. Which is fantastic, because it means when somebody wants to run 2,000 node Hadoop job, you want to do that on my test cluster, go for it. But just be aware that if I want to run something, I'm going to take some of those back. But it gives you really, really great utilization for your hardware. Now, having all of this is great, but what does it actually mean for developers? Because if you're a developer, chances are you don't actually want to interact with all of this stuff day to day. So, we've done something a little bit different. We've automated pretty much everything. So we have automated Bamboo Builder. What it does is it listens to GitHub. So we have a GitHub repository, private, where we store all of our code. And anytime somebody adds or removes a repository to this GitHub account, then wonderful, Bamboo now automatically adds a plan for it. Which means if you're a developer, the second you to actually create the repository on GitHub, poof, there's now a Bamboo plan that will do Dockerized builds for you. Not only that, it will also run tests, and if your tests fail, it's going to send you off an email saying, you may want to. And it does, as I said, the compile, the build, the Dockerization, and the upload. Now, we have coupled this with another technology, which is our auto-deploy system. This is where things get slightly scary, and it's also why it's only enabled for a sandbox data center. Automatic deployments tied to code check-ins is a very bad idea in a production system, because that means the first time a developer pushes to the wrong branch or something like that, oops. But for the sandbox, all of this is okay. So this also listens to GitHub, and if you push to the master branch, it will look for in the branch for a YAML definition for the service. If it can find that, it will wait for Bamboo to finish building. Bamboo, unfortunately, does take about a minute to finish building. But once it's done that, it will then go to Aurora and say, OK, you have this running already. Yeah, stop that. Here's the new Docker image for you. And it will also go update Nginx and say, OK, if there's an external request, please take this and forward it to this Docker image. And that means if I do a git push and I send this off, about a minute later, my service is now deployed and running and hopefully working. Let's go through this. So we have our GitHub. It pushes out, and the second you submit something, this is the Hypermuffin service. We'll try to look at the demo really soon. Bamboo is going to pick this up, as will our deployer. Our deployer is really, really fast, and it's also, it doesn't have a lot of patience. So it really picks this up in about half a second, and then goes talk to the Docker image repository and says, do you have it yet? 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 In fact, most of the traffic to our Docker image repository is the ARB deployer asking if you have it yet. At some point, we should really add a callback there instead. Never mind. Bamboo will, about a minute later, finally push the image, at which point the ARB deployer was like, woohoo, shiny, got it. Now goes to Aurora and says, OK, that thing you had, toss that. OK, here's the new one. Please allocate it really soon, because I just shut down the old one. Yes, this is the sandbox. In the sandbox, it's quite OK to first take down the service, then deploy the new one. Don't do that in production. Aurora will, as we said, talk to Mesos, try to figure out resources, and then say, OK, run it here on my behalf. Mesos at that point contacts the Mesos slave. The Mesos slave runs on the actual node. And at that point, the Mesos slave will go back to the Docker image repository and download it. Execute it and run it. Now, we're going to demo this. The thing is, we ahead of time actually tested the local internet connectivity here. It does, how do I put this?
Some issues.
There are some issues with the local internet connectivity, so I do apologize. We actually recorded this, otherwise we would do it live. So, hopefully, that's interesting. I thought I did. Oh, apparently enter full screen is not the same as enter full screen. Okay. Excellent. So this is our Hypermuffin service. I have pre-prepared git commit here, which is changing this hello world to automation is awesome. Now my timing might be slightly off here since I just recorded this. There we go. So we're going to commit this and push it. Now the next thing we want to do is go have a look at our deployer and see that, okay, yeah, it's there, come on, pick it up, there we go. That's the new definition for the hypermuffin. And you can see it found a new master hash and now says, okay, we want to wait for this. Then we wait for Bamboo, which is going to take a minute. Now, I'll be honest, I actually fast-forwarded the video for this. It does actually take a minute. It's just there's a limit to how much I can say while we're watching a progress bar. But this is a full compile upload to the Docker registry, and there it's done. At this point, the ARB deployer will actually now say, woo, shiny, and go talk to Aurora. I tried to actually capture that. Unfortunately, I wasn't paying attention, so it's already done. So if we go here and reload, let's go say, automation is awesome, yay! That was a full deployment. Actually, if you go to that URL, it should be up and running right now, and it's open to the world. Now, that's cool. Let's take it one step further. This doesn't actually demonstrate anything of this auto-resilience stuff. So let's have a look at the code. What you just saw was the top stuff of this. There's a secondary part for this, which connects to the database. And yes, all this is Node.js. I do apologize for the quality. I am not a JavaScript developer. I just wanted to do something in Node.js. But here you go. It's connecting to our database, which has the hello world. So let's add a row to it. And let's go see. Does that actually come up? Yes, it does. Wonderful. OK, so this is the simplest microservice possible. It's that application and database. And a database. So if I want to demo resilient infrastructure, let's go find this database. And let's figure out what we can do with it. So I just figured out where the machine or where this database is actually running. So logging in there. I need to learn to type faster. And rebooting. Let's just turn it off. So that's an entire machine with tons of stuff running on it, including my database. And off it went. So let's go have a look at how this actually looks for my shell, which is connected to this. Let's add another row. And, ooh, there seems to be a network glitch. Thankfully, automatic reconnection works, and there we go, another row has been added. And the application at this point, well, as soon as I hit reload, come on, there we go. Now we has the additional row. Now, behind the scenes, while we did this, what actually happened is we turned off the machine. Aurora figures out, whoops, my service just died, I'm going to restart it. Okay, where can I restart this? Okay, this machine is available. Okay, I'm going to start a Docker job there, hook it up to the same networking address, hook it up to the same storage. Now, to my shell, which was sitting there, it looks like, for some reason the remote server was temporarily unavailable. There was a network glitch. Somebody moved a cable. That's what it looks like. In reality, the entire thing just moved. For the application, which, because I designed it that way, opens a new connection for every single one, it doesn't even notice that the database has been temporarily down. Let's see. You can actually try all of this out. We have our Docker with storage and networking on the GitHub, as is our Aurora modifications. Soon to be accepted upstream, right?
Yep.
Yep. Pretty soon we'll also put out this the data center in a box, which is this auto provisioning for an entire data center. We just need to remove a few private keys from the GitHub repository. We also have a lot of work done on a level higher above this, which we have not talked about here today, which is the level where you actually want to do service-to-service communication. We do all of our work or most of our work in Java. We're using Thrift for service-to-service communication. It was not great how Thrift does connection pooling and asynchronous communication, so we actually modified that. The compiler for it is open source already. The runtime is still missing. We also use AES GCM, as in SSL, between the services. If you take the Java implementation, it does a whopping 5 megabytes per second of compression, or of encryption, which is really pathetic on a 40 gigabit network, which does 4.5 gigabyte per second of transfer. So we modified it to actually use OpenSSL, and it now does about, or the theoretical bound is about 2 gigabytes per second. So about 400-fold increase. The last is the cluster connect, which is the ability if you have a large microservice cloud. Let's say you have 200 services. If you want to actually develop this, it's kind of difficult to run 200 services on your laptop. So we have the ability to run this in our sandbox data center, pull out one service, run that in your laptop, and hook your laptop up to the rest of the cluster. So that only that service runs on your laptop, and the rest keeps running in your QA data center. And this builds on the routing work we've already done. So all this should be available shortly. We host the Dr. Buenos Aires meetup every month, so please join us there. We also have a front-end meetup and an engineering management meetup. We have Google House and quite a few other things. That's it. Questions?